Today we are going to talk about the Otto cycle, which is a gas power cycle. To represent the cycle, we will draw a TS and PV plot with the path of the 4 stages. Process 1 to 2 is an isentropic compression. In this stage, the air is compressed, decreasing the volume. The entropy remains constant, and since this process is reversible and adiabatic, the heat transfer is equal to 0. Process 2 to 3 is a constant volume heat addition. In this stage, a pressure jump occurs due to combustion. The volume remains constant, meaning work for the process is equal to 0. Process 3 to 4 is an isentropic expansion. In this stage, the power stroke process, the air expands, increasing the volume. Air is expanded isentropically, meaning the entropy remains constant. Since this process is reversible and adiabatic, the heat transfer is equal to 0. Process 4 to 1 is a constant volume heat rejection. The cycle is completed in this process by transferring heat to the surrounding. The volume remains the same, causing the work to equal to 0. Now we will discuss how one can calculate the thermal efficiency for the Otto cycle. Thermal efficiency, or eta, is equal to W dot net over Q dot in. For reversible cycles, W dot net is equal to Q dot in minus Q dot out, where W dot net is the net power output, Q dot in is the heat transfer rate in or to the gas, and Q dot out is the heat transfer rate out or from the gas. Making eta equal to Q dot in minus Q dot out over Q dot in, which simplifies to 1 minus Q dot out over Q dot in. Remember, the first law of Thermo for closed systems is Q heat transfer is equal to delta U change in internal energy plus W work. For the Otto cycle, heat transfer occurs when volume is constant, meaning work is equal to 0. Making Q equal to delta U, which is equal to mass times the change in specific internal energy, delta little u. For ideal gases, delta little u is equal to the integral from T1 to T2 CV dt. And assuming CV is constant, delta little u is equal to CV times T2 minus T1. This makes Qn, which for this case is Q1 to 3, is equal to mCV times T3 minus T2. Q out, which is Q4 to 1, is equal to mCV times T1 minus T4. For the calculation, we will take the magnitude of Q out, which is equal to mCV times T4 minus T1. We can then plug Q in and Q out into our previous equation for efficiency to get eta equal to 1 minus T4 minus T1 over T3 minus T2. Now we will take a look at the 4 stages of the Otto cycle in a piston. The first stage is compression. The piston pushes down, compressing the air, decreasing the volume. There is no change in entropy, and since the process is adiabatic, the heat transfer is equal to 0. Stage 2 is combustion. In this stage, the piston remains in the same position, meaning no volume change. Stage 3 is expansion. In this stage, the piston expands upward, increasing the volume. The entropy remains constant, and since the process is adiabatic, there is no heat transfer. The last stage, stage 4, is cooling. In this stage, the piston remains in the same position, meaning there is no change in volume. An animation can be found at the link below. Take note that in the animation, the piston cylinder assembly is inverted and will move up during compression and down during expansion.